Alright, I guess it's recording. Hi, my name is Kenan Kortan, and today I'm going to present my final project, Differential GNSS Positioning and Absolute Positioning of a Moving Receiver. So let's start the part 1. Part 1 of the project focuses on implementing a basic differential GPS solution using single difference pseudo ranges. The goal is to estimate the relative position between the user and the reference antennas at every epoch, with an expected accuracy on the order of half a meter to 1 meter. Let's continue with the method that I use. I begin by loading the two Renix observation files. From these files, I identify all epochs that both antennas are recorded. And for each epoch, determine the satellites that appear in both receivers' measurements. And differential processing requires at least 4 common satellites. If fewer than 4 are available, that epoch cannot be solved and it is skipped. And then parse the GPS navigation file and extract broadcast ephemerides. Using these ephemerides, I propagate each satellite's position to every epoch. To make this efficient, all satellite ECF positions are pre-computed and stored in cache before entering the main processing loop. And this ensures that every differential solution uses accurately propagated satellite coordinates. And for each epoch, I form single difference pseudo ranges by subtracting the reference receiver's pseudo range from the user's pseudo range. And these differences remove satellite clock errors and significantly reduce the atmospheric effects, leaving a much more stable and geometry-driven relative positioning problem. And next, I built the geometry matrix, or H matrix, which links the satellite geometry to the unknown differential position. For each satellite, I compute the line of sight unit vector from the reference antenna to the satellite. And this vector describes the sensitivity of the pseudo range changes in receiver position. And each satellite contributes to one row to the matrix containing 3 geometric terms and a 4 term accounting for the differential receiver clock bias. This matrix is the core of the linearized measurement model. And using the H matrix and the vector single difference pseudo ranges, solve a linear least squares problem. And this yields 4 unknowns. This time, the differential ACF position delta x, delta y, delta z, and the differential receiver clock bias delta t times c. And the least squares is appropriate because measurements are noisy, and the method finds the solution that best fits all available satellites. And once the differential position is computed, I convert from ECF to ENU coordinates, which provide an intuitive east-north-up presentation. And finally, I compute the RMS errors over time and evaluate accuracy. The part 1 solution achieved the following RMS performance: east 0.59, slight 0.6 meters. North is 1.32 and up is 1.27 meter. Horizontal makes the 1.45 meter. This component performs best while the north and up exhibit larger fluctuations, which is common because geometry is weaker in those directions. To the ENU, okay, my slides just order. Yep. For the ENU time series, show several patterns. East is relatively stable, north and up contain larger fluctuations and clean spikes around epochs 1000, 2000, and 3005. And these spikes occur when satellite geometry changes sharply, typically when the satellite rise or set. Because each epoch is solved independently and no smoothing is applied, the solution is sensitive to such changes. For the clock bias behavior, Plot shows noticeable jumps whenever the set of visible satellites changes. Since each epoch is solved independently, the receiver clock absorbs the geometric changes and the measurement noise, leading to discontinuities and unrealistic drift. And even though part 1 is the accuracy target, it has clear limitations. Both antennas should be treated as moving, but the method implicitly treats the reference antenna as static, and there is no dynamic model. Each epoch is completely independent, and all measurements are weighted equally, ignoring the satellite elevation. The clock bias is unconstrained, leading to discontinuities, and these limitations explain the spikes in the ENU plot and the behavior of the clock bias time series. And, we can return. And next we explain the part 2. The objective of part 2 was to improve the part 1 baseline using a Kalman filter with a constant velocity model. The filter should smooth the noise and stabilize the baseline, and ideally bring the horizontal error into the sub-meter range. I implemented a 7-state Kalman filter. Let me. Okay, what's. Okay, today it's works not well, but okay. Implement a 7-state Kalman filter containing the ENU baseline components, their velocity, ENU baseline components and their velocities, and the differential clock bias. The measurements were taken from the part 1 baseline at each epoch, and I compared filtered versus unfiltered RMS values. However, two major issues prevented meaningful improvement. Let me show the ENU graph. First, the alternative part 1 solution used as input contained modeling errors because the reference antenna position was incorrectly assumed equal to the user antenna, and only a single ephemerides entry per satellite was used for all epochs, and the measurement model incorrectly scaled the clock turn. And the main issue is coming before the aggressive outlier removal artificially smoothed the baseline, and the ENU origin was computed incorrectly. These mistakes caused the part 1 baseline to over smooth and geometrically inconsistent, and second part 2 itself had missing components. The filter was applied directly to ENU rather than the raw pseudo ranges with correct geometry, and the dynamic model was defined in ENU instead of ECF, and clock was not modeled realistically. No innovation getting or measurement filtering was applied. Because of this, Kalman gain remained extremely small, so the filter simply repeated the raw baseline. Thus, the RMS performance before and after filtering was nearly identical, and spikes remained unchanged both on ENU and clock bias graphs. In summary, the Kalman filter behaved correctly mathematically, but the combination of already over-smoothed baseline and incomplete measurement model made real improvement impossible. To neither on the improvements on the part 1 and part 2, I skipped the part 3, so I'll jump for the part 4. The goal of the part 4 was to compute the absolute position of antenna 2 using standalone GPS pseudo ranges and broadcast ephemerides with targets of around 5 meter horizontal and 10 meter vertical accuracy. The algorithm is implemented as standard iterative least squares. Here we go. Extract ranges for each epoch and propagate satellite position using the ephemerides and from the linearized measurement model, and solve for ECF position and clock bias, and lastly convert all the results to ENU relative to the mean position. To looking for the results, they're diverged. However, the solution diverges completely. New components fluctuated by hundreds of thousands of meters, and the root causes were missing critical GPS corrections. Satellite corrections were not applied, and the wrong ephemeris selection led to stale time of ephemeris values, and no atmospheric models were applied. Also, no applied filtering was used. So because of these issues, the pseudo ranges and satellite positions were inconsistent, leading to unbounded least squares updates. And for the conclusion, the structure of a correct single point solver was in place, but without mandatory GPS correction. Converge was impossible, and thus the standalone solution could not reach meter level accuracy. And lastly, this is the clock bias graph, and this is the part 1, part 5. And part 5 aimed to produce a high accuracy absolute position using the combined GPS and Galileo pseudo ranges with weighted least squares, ideally reaching the sub-meter accuracy. And the final result clearly diverged. You can see on the RMS values and on here. The final results are clearly diverged. The causes are GPS and Galileo times were mixed or mismatched. Satellite positions were evaluated using maybe incorrect time of ephemeris references, or clock corrections were missing or incorrect. Also, maybe the weighting between the constellations was inconsistent, and these factors caused the least square solution to diverge instead of converge. Also, here's the clock bias graph. So final summary is across all parts. As a whole parts, as a summary, the project demonstrates which components of the GPS positions are robust and which are extremely sensitive. Part 1 performed well because the differential methods cancel many errors, and part 2 and part 4 failed where essential GPS corrections or correct geometry modeling were omitted. And these results highlight the importance of the accurate satellite modeling and proper timing and rigorous measurement processing in any GNSS algorithm. And that's all. Thank you for listening to me. Again, sorry for this recorded video. Thank you for understanding. Have a good day.